Hello, I'm Sean Jordan, and I will be presenting Lab 1 for Physics 2211, Constant Velocity. The purpose of this experiment is to observe and analyze the motion of an object moving at constant velocity and in a single path. We will be doing this by utilizing both a physical and computational rendition of the experiment. For this lab, we will be exploring a few key fundamental principles. Newton's first law, which states that an object in motion stays in motion unless acted upon by an external interaction. Newton's second law, which states that an object's acceleration is dependent on the forces on the object as well as its mass. Lastly, we will be looking at the idea of constant velocity, which denotes that an object will move at a constant change in position with a net force of 0. The objectives of this experiment is to measure the motion of the object, compare it to the computational model, which was coded in GlowScript, and expect the position to have a constant rate of change. The way this data will be gathered is through a program called Tracker. Moreover, we will state that the system of the experiment is the rolling object, in my case a dumbbell, and state that everything else will be the surroundings. A few formulas will be needed to aid in the updating of our velocity and position as the object rolls. Using Newton's second law, we have the velocity update formula and the position update formula. We also will use the formula for average velocity, which is needed to find the velocity of the object as it rolls. Here we have the video analysis and tracker of the rolling object. The origin starts at my chosen state after I've let go of the object. This means that at the point of the origin is where the time will start. It is also important to note that the object is moving in the positive x direction, which is supported by the graph shown in the top right that has a positive slope. Here is the data that is gathered from the observed tracker model. Firstly, the video was shot in 30 FPS. Mean that the change in time per frame is roughly 0.033 seconds. The initial position and time were gathered at the placed origin and are both roughly 0. The velocity was calculated from the previous formula and can be seen in the calculation at the bottom of the slide. Last, the time frame of the rolling object in tracker was about 1 second or 1.001 seconds. The initial conditions found from the tracker model get placed into the computational model seen here. The initial position and velocity are both the starting position and the average velocity respectively, as this would be the main vectors that will be iterated upon. The start time for the rolling was at 0 seconds, and the delta t will be the time per frame of the video, which is, again, 0.033 seconds or 1/30. The mass of the object does not matter for this experiment, as this number will amount to 0 due to the net force being 0 when in constant velocity. Following up with the actual iteration, it will draw the graph up to 1.001 seconds, the same time that the tracker model was also ended up at. The net force will be 0 as, again, the object will be rolling at constant velocity. Next, we need to apply Newton's second law by using the position and velocity update formulas in a coded context to map out each data point as time progresses. Here we see that both versions constitute each other in their respective variables found from Newton's second law. Making a plot comparing the observed and predicted models of the rolling object, we see that initially both have similar velocities. However, as the time progresses, the observed position starts trailing off downwards. This was caused mostly due to forces acting upon the object in the opposite direction, making it slow down. Some potential errors for this experiment are human errors when setting the center of mass in the tracker program, which can slightly skew data points. Also, the observed model does not account for slight changes in motion, also skewing the data points. Now, what if the axis were to be flipped? Well, the data would then be reflected across the x-axis. This would cause a change in position and velocity to change signs depending on what direction you made the tracker model based upon. In my case, it would have been the negative slope rather than the positive slope. Despite this, the magnitude of both the position and velocity, regardless of the flipped axis, will stay the same. Is it possible to determine how many pushes and pulls on the object to get a net force of 0? The answer is no. Because there is already a net force of 0 on the object, that being the cancellation of the force due to gravity by the normal force of the object held up by the ground, other forces will be much more difficult to figure out as the object rolls. That is the end of this presentation. Thank you.